Here we discuss the convergence of gamma integration. Okay, this is very important integration of improper integral. And what is gamma integration? The gamma integration or gamma function, this is denoted by gamma n. This is the symbol of gamma. This is equal to integration 0 to infinity e to the power minus x into x to the power n minus 1 dx. And we try to prove this integration is convergent for n greater than 1. Right? Otherwise not convergent. To prove the convergence of gamma integral, we here use 4 results. The first result is, we all know these 4 results. The first result is integration a to b dx by x minus a whole to the power mu is convergent if and only mu less than 1. Here a that is the lower range x equal to a is the point of infinite discontinuity only. Okay, and the second result is integration a to infinity dx by x to the power mu is convergent only if mu greater than 1. And here the essential condition is a, the lower range is greater than 0. Right? These two tests or these two results look like similar, but there are huge difference because this is convergent for mu less than 1 and this is for mu greater than 1. And 3 and 4 are the two part of same test. This is comparison test. If integration a to infinity fx dx less equal to integration a to infinity gx dx, and if integration a to infinity fx dx convergent if this integration is convergent, because the larger integration is convergent, then the smaller integration must be convergent. And the last result is comparison test of limit form. If limit extends to a plus sorry, fx by gx, this is equal to L, where L not equal to 0, that is non-zero finite, not equal to 0 and not equal to infinity. Then integration a to b fx dx and integration a to b gx dx behave likely, or together either divergent or together either convergent. And if we know the integration of one function, then this is the same behavior as the other function. Okay, this is the comparison test of limit form. Now we go our original problem. Here this function is equal to 0 to infinity e to the power minus x and x to the power n minus 1 dx. Clearly, if n less than 1, okay, then x to the power n minus 1, this is in the denominator. Okay, so this integration has point of infinite discontinuity at x equal to 0. Also, at the upper range of the integration, the range of the integration is infinity, so there be another improperity. So we first split this integration into two parts. The first part is integration 0 to 1 e to the power x and x to the power n minus 1 dx, this is minus, and the second integration is 1 to infinity e to the power minus x, x to the power n minus 1 dx. We may write this is 0 to 2 and 2 to infinity, or 0 to 3, 3 to infinity. The problem is same, and as usually we know, or we write here, this is 1, this is 1. Okay, as 1, this the same proof for 2, for 3, or for 4, 5, etc. Okay, now we name this integration is I1, this integration is I2. For I1, this is equal to integration 0 to 1 e to the power minus x, x to the power n minus 1 dx. If n greater or equal to 1, then I1, this is I1 I1 is proper, because if n greater equal to 1, so 0 and 1 both are the not point of infinite discontinuity, and there be no other point of discontinuity for this function. So this is proper integration, that is convergent. Now if n less than 1, right, then n less than 1, then we write this integration as integration 0 to 1 e to the power minus x into x to the power 1 minus n, because 1 minus n greater than 0 here. Okay, and in this case x equal to 0 be the point of infinite discontinuity. Clear? X equal to 0 be the point of infinite discontinuity. And this is integration 0 to 1 fx dx, and let gx be another function as x to the power n minus 1, or this is taken as 1 by x to the power 1 minus n, right? Then by using comparison test of limit form, that is the result 4, we say that limit x tends to 0 fx by gx, this is cancel out the term 1 by x to the power 1 minus n and 1 by x to the power 1 minus n, we get this is equal to e to the power minus x. So e to the power minus 0, that is 1, that is finite. Okay, so both the integration have same behavior. Now we know that integration 0 to 1 by x minus 0 whole to the power 1 minus n dx. Okay, this integration look like the first integration, the first result, and this is convergent if and only mu less than 1. So it is convergent if and only this is mu, so this is 1 minus n less than 1, that is n greater than 0. And we say that for the case of I1 is convergent only if n greater than 0. Okay, this is the first result, or this is the result for I1. Now we start to test for the integration I2. 1 to infinity e to the power minus x into x to the power n minus 1 dx. Clearly from the range it is say that x greater than 1. Now we expand e to the power x in an infinite series. And since x greater than 1, so we expand this result as 1 plus x square by factorial 2 plus x cube by factorial 3 plus 2x to the power r by r factorial to infinity. Okay, here x greater than 1. And since x greater than 1, we can write this result as e to the power x greater than x to the power r by r factorial. We get any term from this infinite term. We take here x to the power r by factorial r in such way that we choose r such that r minus n plus 1 greater than 2. Okay, we choose here r minus n plus 1 greater than 2. What is the function of this choosing r? Since e to the power x greater than x to the power r by factorial r, so we can write e to the power minus x less than r factorial by x to the power r. We taking reverse or reciprocal on both sides, right? And multiply both sides by x to the power n minus 1. And e to the power minus x into x to the power n minus 1, and this is less than r factorial by x to the power r into x to the power n minus 1. and this is given by r factorial by x to the power r minus n plus 1, and clearly r minus n plus 1 is greater than 2. So if we put in this position is 2, then this is also greater than this term. Sorry, this is x square, because x greater than 1 and r minus n plus 1 greater than 2. So x to the power r minus n plus 1 greater than x square, and taking reciprocal on both sides we write this result. Okay, and now taking integration 1 to infinity on both sides, we get integration 1 to infinity e to the power minus x to the power n minus 1 dx. This is less than integration 1 to infinity r factorial by x square. This is x square dx. And clearly from the second result, this is a to infinity and dx by x to the power mu is convergent. This result is also if and only mu greater than 1. And in this integration, if we write factorial r on the outside of integration, then here mu this is equal to 2 greater than 1, and here a this is equal to 1 must greater than 0. So we say that by using this integration, the right side integration is right side integration is convergent. And we use the comparison test in general form. This form may be written in the form integration a to infinity fx dx less equal to integration a to infinity gx dx or k into gx dx, where k be a positive constant. Then the result same hold. So by using the condition 3 or comparison test, we say that this integration is convergent. So by comparison test, I2 is convergent for any value of n. Okay. So for I2 there is no restriction of n, that is for all n belongs to capital N, or for all n belongs to capital R maybe. Clear? So for the first integration, the restriction of n is n greater than 0, and there is no restriction for n in the second integration. So we say that the gamma n or gamma function or gamma integration is convergent only when n greater than 0. Right? This is the proof of convergence of gamma integral, and this is very important for your exam, and this is one of the most important example or exercise or problem of improper integration. Okay, thank you for watching.